Okay, hi everyone, and welcome back to day 3 of Intro to Deep Learning. Today is a really exciting day because we're going to learn how we can really try to fuse two really important topics in this field. So we're going to look at how we can marry these two topics of reinforcement learning with deep learning, which is the main topic of this class. So this field, this marriage between these two topics is really exciting because it moves away from this paradigm completely that we've seen so far up until this day in this class to date, right? So instead of deep learning, instead of the models that we train in deep learning being shown fixed data sets that don't change over time and supervising them, teaching them based on these data sets, we're now going to look into problems that involve the deep learning model exploring and interacting with the data sets in a dynamic way so I can learn how to improve based on these scenarios and these environments that they're being placed in dynamically and evolve over time. And the goal, of course, is to do this entirely without any human supervision. So previously, our data sets were largely being created through some supervision of humans. But now we're going to look into scenarios where these models are interacting in an unsupervised manner with their environment and can actually, because they're not being constrained by human supervision, can actually learn to go to superhuman performances. So this has huge obvious implications and impacts in many fields. And just to name a few, there's robotics, self-driving cars, but also on the other side, there are strategic scenarios with game playing and also with problem-solving scenarios as well. So we're going to get a huge flavor of all of these different types of topics and how we can deploy these new types of algorithms and these new settings in these different types of environments. So to start, I just want to take a step back and see how... Yes, go ahead. Yes. Okay, they'll be up soon. Okay, so I want to start and just take a step back, first of all, and think about how this topic of reinforcement learning is different at a high level from all of the other topics that we've seen so far in this class, right? So in day 1, we focused primarily on this class of learning problems called supervised learning, right? So in supervised learning, which was actually day 1 and also the first lecture in day 2, it covers this domain where the input label, where the input data X, and you have also output labels Y. Now, the goal of supervised learning, as we saw in those first 3 lectures, is really to try and learn a functional mapping that can go from X to Y, right? So you showed a bunch of examples of input data, you showed a bunch of labels Y, and you want to build some function in the middle that can transform X into a reasonable Y. So, for example, this is like if I showed you this picture of an apple on the bottom, and you were to classify this picture as this is an apple, right? So that's supervised learning. You showed a bunch of these pictures, you train it to say, okay, these are apples, these are oranges, these are bananas, and when you see a new picture of an apple, you have to correctly classify it. In the last lecture of day 2, we discussed a completely new paradigm of problems called unsupervised learning problems, and this is where you only have access to the data. Only the X's. You don't have any Y's. You don't have any labels. And you want to try now to learn a model, not to transform X's to Y's, X's to labels, but now you're just trying to learn a model that can capture the underlying structure of X, of your original data. So for example, going back to the apple example on the bottom, using unsupervised learning, we can now show our model a lot of data of these types of different images, and the model should try to learn how to essentially cluster them into different categories, right? So they should put images that look similar to each other, close to each other in some space, in some feature space or latent space, as we saw yesterday, and things that are dissimilar to each other should be very far away, right? So the model here doesn't know anything about that this thing is called an apple, but it recognizes that this thing shares similar features to this other thing, right? And they should be close to each other. So now, today's lecture in reinforcement learning, we're going to talk about yet another completely new paradigm of learning problems for deep learning. And this is called now where you have data not in the form of inputs and labels, but you're going to be shown data in the form of states and actions. And these are going to be paired pieces of data. Now, states are the observations of your agent. We'll get back to what those terms mean in a second. And the actions are the decisions that that agent takes when it sees itself in a certain state. So the goal of reinforcement learning, said very simply, is to create an agent, to create a model that can learn how to maximize the future rewards that it obtains, right, over many time steps into the future. So this is, again, a completely new paradigm of learning problems that we've seen before. There are no ground truth labels in reinforcement learning, right? You only have these state action pairs, and the objective, the goal, is to maximize some reward function. So now in this apple example, one more time, we might see this picture of an apple, and the agent would have to learn, to eat this thing because it has learned that it gives it some nutrition and it's good for it if it eats this thing. Again, it knows nothing that this thing is an apple. It knows nothing about kind of like the structure of the world, but it just has learned some actions to do with these objects by interacting with the world in a certain way. So in today's lecture, that's going to be the focus of what we talk about, and we'll explore this in greater detail. But before we go any further, I think it's really important for us to dissect and really understand all of the terminology, because this is a new type of learning problem, there's a lot of new pieces of terminology that are associated to reinforcement learning that we don't really have in supervised learning and unsupervised learning. So I want to start by firstly building up some vocabulary with everyone such that it will be necessary for the rest of this lecture, and we'll keep referring back to all of these different pieces. So I'll start with an agent. An agent is something that can take actions, right? So for example, in let's say autonomous delivery of packages, a drone would be an agent, okay? In Super Mario games, Super Mario would be the agent, right? It's the thing taking the actions. The agent, or the algorithm itself, is the agent, right? It's the thing that takes the action. So in life, for example, we are all agents. The next piece of vocabulary is the environment. You should think of this as simply the world in which the agent lives, and it can take actions in. And the agent can send commands to its environment in the form of these, quote, actions. And we can also denote, just for formality, let's call A the set of all possible actions that this agent could possibly take. So in a very simplified world, we could say that this agent, let's say it's in a two-dimensional world, it can move forwards, it can move backwards, it can move left, it can move right, right? So the set of all possible actions are these 4 different actions. Okay, now coming back in the opposite direction, observations are simply how the environment interacts back to the agent. So observations are states, essentially, that the environment sends and shows to the agent, and how an agent observes the world. Now, a single state is just a concrete and immediate situation in which the agent finds itself in, right? That's the immediate observation that the agent is present in. And finally, here's another new part, specifically towards reinforcement learning, is the reward. So in addition to providing a state from environment to action, the environment will also provide a reward. So a reward is simply the feedback which we can measure, or which the environment provides to measure the success or the failures or the penalties of the agent in that time step. Okay, so what are some examples? So in a video game, when Mario touches a gold coin, the points go up, right? So he gets a positive reward, right? Let's see, what are some other examples? So if he were to jump off the cliff and fall to the bottom, he gets a very negative reward, right? Penalty and the game is over. Okay, so rewards can be both immediate, in the sense of the gold coin, right? Touch the gold coin, you get an immediate reward. But they can also be delayed, and that's a very important concept. So you may take some actions that result in a reward much later on, but they were critical actions that you took at this time step, and the reward was delayed, and you don't recognize that reward until much later. It's still a reward, and that's a very important concept. So we can now look at not only the reward at one time step, which is R of t. But we can also look at the total reward, which is simply, you can think of the sum of all rewards up until that time. Okay, so we'll call this capital R of t. That's just going to be the sum of all of the rewards up until time t. So from time 0 to time t. If we expand it, it would look like this, right? So it's the reward of time t plus the reward of time t minus 1, and so on. So often it's useful to not only consider the reward at time t, right, or the sum of all rewards up until that time, but also to consider the discounted, what's called the discounted reward over time. Okay, so what does that mean? So the discount factor, which here is denoted as this gamma term, okay, so it's typically a fixed term, so you have one discounting factor in your environment, and your environment provides that. Typically, you can think of the discounting factor as a factor that will dampen the effects of a reward over time. Okay, so why would you want to do this? Essentially, a discounting factor is designed such that it will make immediate, or let me say, it will make future rewards much less, worth much less than immediate rewards. Okay, so what's an example of kind of an example where you have this enforcing of a short-term learning on an agent, right? So, for example, if I was to offer you a reward of $5 today or a reward of $5 in 1 year, it's still a reward of $5, but you have an implicit discounting factor which allows you to prioritize that reward of $5 today over the reward of $5 in 1 year's time, right? And that's what the discounting factor does. The way you apply it in this framework, though, is that you multiply it by the future rewards as discovered by the agent in order to dampen all of the future rewards that the agent sees. Now, again, this is just meant to make it such that the future rewards are worth less than any of the immediate rewards that it sees. Okay. Now, finally, there's one more really important concept that's critical to understand as part of all of this, and that's called the Q function. Now, and yeah, I think it's also critical that we think about the Q function in the context of all of the previous terminologies that we've covered so far. So let's look at how the Q function is defined in relation to all of those previous variables that we had just explored. So remember that the total reward, it's also called the return of your agent. The return is capital R of t. So that's the discounted sum of rewards from that time point on. Now remember that the Q function now is a function that can take as input the state, the current state that you're in, and a possible action that you take from this state, and it will try to return the expected total future reward, or the return of that agent that can be received from that time point up until the future. Okay, so let's think about that a little bit more, just digest it. So given a state that you're in and an action that you take from that state, the Q function will tell you what is the expected amount of reward that you will get from that point on if you take that action, right? Now, if you change the action, A of t, in the current state, your Q function will say that, okay, this is actually going to return you even more reward, or maybe even less reward, right, than the previous one. So this Q function is actually a critical function that allows you to do a lot in reinforcement learning. So now the question is, I guess, if we're, for now, assume that we're given this magical Q function, right? I give it to you, and you can query it, you can call it at your desire. How can we, as an agent, so put yourself in the agent's point of view, and I give you the Q function, how would you take actions to solve an environment, right? What actions would you take in order to properly solve this environment? So any ideas? Yes?
Just keep maximizing the Q function.
Right, so what actions would you take? You would take the ones that would maximize the Q function, right? So at every time point, ultimately, what you have to recognize as the agent's point of view, right, is that every time step, you want to create some policy, right? So what we're thinking of here is now this policy function, which is slightly different than the Q function. So the policy function will denote it with a pi. It only takes as input s, and it's going to say, what is the optimal action that I should take in this state? So we can actually go from, or we can try to evaluate the policy function using the Q function, right? And as was stated, this can be done just by trying to choose an action which maximizes the future return of that agent, right? So the Q function, the optimal policy function, pi, how to act in a current state, S, is simply going to be defined by taking the action which gives you the highest Q value, right? So you can evaluate all possible actions from your Q function and pick the action that gives you the highest return or the highest future reward. Now, in this lecture, what we're going to focus on at a high level is really looking at two different ways that we can think about solving this reinforcement learning problem and thinking about this Q function in specific, right? So there are two broad categories which we're going to think about in terms of learning this Q function, right? Because so far I've only said if I give you the Q function, I haven't told you actually how we create that Q function. And basically these two categories can be split up such that on one side we have value learning algorithms, and on the second side we have policy learning algorithms. So the second class of algorithms, these policy learning algorithms in particular, are directly trying to learn not the Q function, as we previously said, but they're directly trying to learn that final policy function, right? Which, if you think about it, is a much more direct way of accomplishing your goal. Ultimately, what the agent wants to do is see a state and know the action to take in that state, right? And that's exactly what the policy function gives you. But first, let's focus on the value learning side of things. And we'll cover that, and then we'll build up our foundations to go to policy learning. So in order to cover value learning, we have to first start by digging a bit deeper into this Q function, right? This is a really critical function, especially when thinking about the value learning side of the problem. So first I'll introduce this Atari breakout game. Probably many of you have seen it before, but in case not, I'll just quickly describe it. So the concept of the game is that the agent is this paddle, this horizontal line on the bottom. It can take two actions, roughly. It can move left or it can move right, or it can also stay, not move at all. But for simplicity, let's just say two actions, left or right. And the environment is composed of this, two-dimensional world. It has this ball that is being a projectile. It's coming towards the paddle. And the objective of the paddle is to basically move left and right to reflect and bounce the ball off, because you want to hit as many of the blocks as possible on the top. Every time you hit a block on the top, those colored blocks, you will break off a block and you get a point. So if the objective of the game is actually to remove all of the colored blocks on the top, you can do that by keep moving around and keep hitting the ball and breaking them off one at a time. So the Q function here is going to tell us the expected total return of our agent such that we can understand how, or we can expect, which, given a certain state, right, and a certain action that this paddle could take at that state, right, and which of the rewards or which of the actions would be the optimal action to take, right? Which of the actions would be the one that returns the most in expectation a reward by breaking off as many of those blocks on the top as possible, right? So let me show just a very quick example, right? So we have these two states and actions, okay? So for every state, you can also see the desired action by the paddle. So here's state A, which is where the ball is basically coming straight onto the paddle, and the paddle chooses the action of not moving at all, right? Just reflecting that ball back up. And we have state B, which is the ball coming in at an angle, almost missing the paddle, and the paddle is moving towards the thing. It might miss it, it might get it, but it's trying to catch up and grab that paddle. Between these two state action pairs, right, so they each have, or they can each be fed into the Q function, And if we were to evaluate the Q value of each of these state action pairs, a question for all of you is, which state action pair do you think will return a higher expected reward for this agent? Which one is a better state action pair to be in? Any ideas, A or B? So let's see, between A, raise of hands. Okay. B? Okay. So someone that said A, can we explain the answer? Hands? Okay. Yep.
Well, it seems pretty safe. You will not lose your ball, you just pump it back, and obviously there will be some breaks there, and you can break them and get some points.
Exactly. So yeah, the answer is it's a very safe action. It's very conservative. You know, you're definitely going to get some reward from this state action pair. Okay. Now, what about B? Anyone answering for B? Yep.
If you choose B, there's a possibility that it could ricochet and like you can hit more blocks. With A, it just bounces up and down, and you get a minimum amount of points, but you can probably exploit it going around if you can get it above.
Yeah, exactly. So yeah, the answer is basically B is a bit more erratic of a state action pair, and there's a possibility that some crazy things could happen if you have this very extreme, fast-moving thing that comes off to the side. So this is just a great example of why determining the Q function, learning a Q function, is not always so obvious, right? So it's a very intuitive answer would be A, but in reality, we can actually look at how a policy behaves in two of these different cases. So first, let's look at a policy that was trained to maximize situations like A. And we'll play this video forward a little bit, right? So this is a very conservative policy. It's usually just hitting the balls straight back up to the top and learning to, solve the game. It does break off the balls, or break off the colored things on the top, but it's doing it in a very conservative manner, right? So it takes some time. Now let's switch over and let's look at B, right? So B is having this more erratic behavior, and it's actually moving away from the ball just so that it can come back towards it and hit it with that extreme value, just so it can, break off something on the side, get the ball stuck on the top, and then break off and get a lot of free points, basically. So it's learned kind of this hack to the system in some ways, right, to uncover this, right? And it's just a good example of, the intuition behind Q values for us as humans is not always aligned with, what the AI algorithms can discover during reinforcement learning. So they can actually create and find some very interesting solutions. Maybe they are not always exactly as we expect. So now let's see if we know that Q function, right, then we can directly use it to determine the best action that the agent should take in that scenario, right? We saw how that was possible before. The way that we would do that is we would take, all of our possible actions, we would feed them through the Q function one at a time, evaluate the Q value for each of those actions, and then be able to determine which action resulted in the greatest Q value, right? So now, how can we train a network to determine the Q function, right? So there are two different ways that we could even think about, structuring and architecting such a network, right? We could have the state and the action be inputs to our system, and then we output a Q function, a Q value for that state action pair. That's going to be basically how you see on the left-hand side. So it's a single number for a state and an action input to the network. Or you could imagine something on the right-hand side, which probably is a bit more efficient, right? Because you only feed in a state, and then the model has to learn the Q value for each of the possible actions. So this would work if you have a fixed and small set of actions, right? If you're only going left or right, your output would just be two numbers, Q value for left, Q value for right. And often it's much more convenient to do it like this, right? Where you just output the Q value for all of your actions, just so you don't have to run your network multiple times with multiple different action inputs. So how can we actually train this, what's called deep Q network, right? It's a network that learns the Q value. We should think about first the best case scenario of our agent, right? So how would our agent perform in the ideal scenario, right? What would happen if the agent were to take all of the very best actions, right? At each step, it's taking the best actions that it could. This would mean that the target return, right, this Q function, or this Q value, I should say, the Q value would be maximized because it's taking all of the optimal actions. And this would essentially serve as the ground truth to train our agent, right? So our agent is going to be trained using a target Q value function, which is going to be assumed to be the optimal one, the one that maximizes all of our agent's action, or agent's Q values. Now, the only thing left now is we have to, use that target to train our predicted Q value, right? So to do this, now all we have to do is formulate our expected return, our expected Q value, where we take all of the best actions, right? So that's the initial reward that we start with. We select an action that maximizes the expected Q value at that point. And then we apply that discounting factor. We compute the total sum of returns from that point on. And then we use that as our target. And now all we have to ask is, what would the network predict in this case so that we can learn to optimize this, right? And of course, for our network prediction, that's a lot easier because now, at least in the second example, we have formulated the network to directly tell us the predicted Q value for each of these actions, right? So we have a prediction as desired, and now all we have to do is formulate, a mean squared error, subtract these two pieces between the target and the prediction, compute a distance from them, so maybe we square them, compute the norm, right? And then that's the piece that we want to minimize, right? We want to minimize the deviation between the predicted Q value coming from our model and kind of that target Q value, which is obtained on the left-hand side. So this is known as the Q loss, and this is exactly how Q networks, deep Q networks, are trained. So let's take a second now and just summarize that whole process end to end, because that was a lot in there. So our deep neural network is now going to see only states as inputs, and it's going to output the Q value for each of the possible actions, right? So here we're showing 3 actions: going left, staying stationary, and going right. So our network will have 3 outputs. It will be the value of the Q value for each of those actions taken with this input state. So here, the actions again, left, right, or stay stationary. Now, the policy, how an agent would act in this state, right? If you now see a new state, you have to figure out what action do you take. You take all of your outputs, all of the Q values, you pick the maximum one because that's the one that has the highest expected return, at least predicted by your network, and you pick the action that corresponds to. So for example, here we have Q value of 20 for moving left, Q value of 3 for moving stationary, and Q value of 0 for moving right. So here we would pick the action of left, right? And finally, we would send this action back to the environment. We would actually take that left action. The state would update through our game engine, right? So we will now see a new state, and then this process will repeat again, right? And then the network will have to receive this new state, process all of the Q values for that possible action, for those possible actions, and then pick the best one again. Yes?
What about when the action is not one specific value, but it's a ring?
Yeah, we'll get to that in a second. Yeah. Yes.
So do we compute, let's say, Q of S and B in one step, or we have to play the game until it ends?
Great question. So you actually have to compute it every step, right? Because you have to know, you can't play the game until you know what to do on the next step, right? So you see a state, you need to do something, right? So the thing that you do has to require running this Q network so that you can compute the action. Right, so that's why you have to train the network. So in the beginning, these networks, they don't know anything, right? They're going to output gibberish as their Q values, right? And that's why you actually have to train it using the Q loss. So over time, those values will improve, and over time, you're going to predict better and better actions. Great. Yep.
How do you know when to obtain the next state? So for example, if you go to the left, the ball might just bounce around really wackily for a while. And then at some point, you would need to read the state, but you might end up reading it prematurely and doing something that's suboptimal because the ball is still up in the air or whatever.
Right. So the question is about when to update the state, as I understand it, right? So the state update. So this is happening by the environment, actually. So you don't have control of that, right? So you send an action, the game always updates the screen, right? So that's your new state, right? And you have to make a new action. You don't have a choice, right? Like, so even doing nothing is an action, right? Being stationary is an action. So that is kind of not up to the agent, right? Life goes on even if we don't take actions, right? And the states are constantly changing regardless of what we choose to do. Okay, so with this framework in mind, right, we can now see a few cool examples of how this can be applied. So a few years ago, DeepMind showed actually the first really scalable example of training these types of deep Q networks and how they could be applied to solve not just one type of game, but they actually solved a whole variety of different types of Atari games by providing the state as an input on the left-hand side. Okay, and then on the right-hand side, it's computing the output, the Q value output for every possible action. You can see here, it's no longer 3 possible actions, right? This is from like a game controller, right? So you have a bunch of different actions, right? Still not a huge number of actions. We're gonna think if like the action space is really large, how can you build these networks to handle that? But for now, I mean, this is already a really impressive result because what they showed was that if you test this network on many different games, and in fact, all of the Atari games that existed, they tested on, they showed that for over 50% of the games, right, these deep Q networks were able to surpass human performance, right? Just with like very basic, algorithm that we talked about today, using a basic CNN that takes as input just the pixels on the screen of an Atari game, with no human supervision, no ground truth labels. The agents just learn how to play in these games. They play basically, a game. They update and they reinforce their learning, and they evolve over time. And just using that algorithm that we talked about for deep Q learning, they were able to surpass 50% of the games surpassed human performance. The other games were more challenging, so you can see those on the right-hand side. They were more challenging, but given how simple and clean this algorithm is that we've just talked about in this lecture, it's still remarkably impressive, to me at least, how this thing even works and beats humans for even 50% of Atari games. Okay, so now let's talk very briefly about downsides of Q learning. So a couple were already mentioned just organically by some of you already, but let's talk about it now more formally. So number one, the complexity, right? So the model scenarios where Q learning can work in this framework that we've just described really involve scenarios where the action space is very small, and also, even more important, the action space has to be discrete, right? So it has to be a fixed number of action categories, right? It's not saying, so the actions would have to be like left versus right. It's not how fast to move to the left or how fast to move to the right, right? That's a continuous number, it's a speed, but it's not a discrete category, left, right, okay. The other one is the flexibility, right? So in policies, in the Q value case, the Q values are needed to compute your policy, right? Your policy, remember, is the function that takes as input a state and computes an action. So that function requires your Q value, your Q function. And it's done by just maximizing that Q function over all of the possible different actions. So that means that inherently you cannot learn stochastic policies with this type of framework that we've discussed so far, right? The policies have to be deterministic because you're always picking that maximum. So to address these kind of challenges, let's now move on to the next part of the lecture, which is going to be this second class of reinforcement learning algorithms called policy learning or policy gradient algorithms, right? So again, in this class of algorithms, now we're not going to try and learn the Q function and use the Q function to compute a policy function. We are directly going to try and find the policy function. So pi of s, it's a function that takes as input the state, and you compute or you sample an action by sampling from that distribution of the policy. Okay, so to cover this, again, very briefly reiterate the deep Q function networks. So here, state comes in, all of the Q values for all of the actions come out, and you pick the action which maximizes your Q value. Now, instead of outputting your Q values, what we're going to do now is directly optimize a policy function. Okay, so our policy function is going to also take as input our state, right? So the input here, the architecture so far is the same that we saw before, right? And pi of s, which is going to be our policy function, that's our output. That's going to be the policy distribution, right? Let's now think of it as a probability distribution, which governs the likelihood that we should take any action given this state. Okay, so here the outputs are going to give us a desired action, or I should even say the likelihood that this action is the best action given the state that we are in. So this is actually really nice because the outputs now are probabilities, right, which has a few nice properties, because those probabilities that an action is the one that we should take tells us very important things about our state. So if we were to look and predict these probabilities for this given state, let's imagine we see something like this, right? So if we were to see 90% the left action is the best possible action we could take, 10% that doing nothing is the best thing, and 0% that going right is the best thing. We can aggregate these into a prediction function, which is essentially now we want to compute our action. How would we do that? We would not take the maximum anymore. Now what we're going to do is sample from this probability distribution, right? So even with this same probability distribution, if you ran it 100 times, on expectation, 10% of them should not be the maximum, right? About 10% of them should have the agent stay still. So note that, again, this is a probability distribution. So all of those action, or all of those outputs have to sum to 1. And I want to spend a moment here, and maybe this is a question for all of you, what are some advantages, or especially from the flexibility side right now, of formulating the architecture in this kind of way? Does anyone see any concrete advantages? Yes?
We could potentially learn some amazing new technique that maybe we couldn't think of ourselves.
Right. So the idea is it can learn some things that we couldn't think of ourselves. This is true, and the reason is because the sampling of these actions is now going to be stochastic, right? You're not always picking what the network thinks is the best action. You're going to have some more exploration of the environment, right? Because you're going to constantly sample. Even if your answer is like this 90%, 10%, 0%, you know, you'll still pick the non-maximum answer 10% of the time, right? That allows you to explore the environment a lot more. Yes?
So for non-zero-sum games, policy gradient would be preferred?
So you could actually use both types of algorithms in non-zero-sum games, but what you would want to make sure is, you know, from a flexibility point of view, right? So the differences that we're seeing so far are much more focused on the actions and the sampling of those actions, right, than the environment itself, at least so far. Yes?
There's a fundamental thing here that when you say Q originally is an expectation of, you know, S, you give me an S today, and then how can you calculate an expectation unless you calculate over some distribution or some assumed form of the future? So I'm missing how you can have a well-defined Q, let alone a pi, without specifying what you mean by expectation value over the future, because there's so many different possible features.
Right. So yeah, this is where the Q learning and policy learning differ greatly, right? So in the Q learning side, you do have an expectation because you do actually roll out the whole game until the end of the game, right? In the policy learning side, there is no expectation except from the point of view that you have this now distribution over the different actions that you can take, and that gives you an expectation as well. But that, you know, that's separate, right, from the Q learning side. Okay. So getting back to the advantages of policy learning over Q learning, right, and digging into this a bit deeper. So one advantage here is just in the context of discrete versus continuous, which was mentioned earlier in the lecture, right? So discrete action spaces, what does that mean? It means that we have a finite set of possible actions that could be taken at any possible time. So for example, we've been seeing this case of Pong, right, or breakout, right? And the action space is indeed discrete. You can go left, right, or stay stationary. But let's assume I reformulate the actions of this game a little bit, and now I make them continuous. So now instead of left, right, or nothing, I'm going to make it a speed at which I should move on that horizontal axis. So now if we were to plot kind of the probability of any possible speed being the best speed that will maximize the reward of this agent, it might look something like this, right? It's going to be a now continuous probability distribution as opposed to a discrete categorical distribution that we saw previously. So let's dig into that key idea, right, and think about how we could define these types of continuous policy learning networks as well. How can you have your model output a continuous distribution, right? And we can actually do this using the policy gradient method. So instead of predicting a probability of taking an action over every possible state that you could be in, let's instead learn a parameter or the parameters of a distribution which define that probability function instead. Okay, so let's step through that a bit more. So in yesterday's lecture, we learned how that our latent spaces could actually be predicted by a neural network, but those are continuous latent spaces over Gaussian random variables, right? We're not learning the PDF over every possible Gaussian random variable, but instead we're just learning the parameters, the mu's and the sigmas that define those Gaussians. So now let's do something similar. Instead of outputting the probability for every possible action, which in a continuous action space, there are an infinite number of possible actions, now let's learn a mu and a sigma that define the probability distribution for us. So for this image, for example, that we see on the left-hand side, we can see that the paddle needs to move to the left. So if we plot that distribution predicted by this neural network, we can see that the density lies on the left-hand side of the number line, right? And it's telling us not only that it should move left, but it also tells us some information about, how quickly or with what speed or with what urgency it needs to move to the left. So we can now sample, not only inspect this distribution, but we can now sample from that distribution to get a concrete action that the paddle should execute in this state. Right, so if we sample from this Gaussian with mean -1 and standard deviation 0.5, we might get a value, for example, like this, which is -0.8. Okay, so it's just a random sample. Every time you sample from this distribution, you'll get something different. And again, even though this is a continuous extension of the same ideas that we saw previously, it still follows that this is still a proper probability distribution. So if we were to take the integral over this probability output of the neural network, its integral would sum to 1, right? This is a valid probability distribution. Okay, so let's now turn to look how policy gradients could be applied in a concrete example. So let's revisit kind of this RL terminology learning loop that we had looked at earlier in the lecture, and let's think of how we could train now this use case, right? So let's imagine we want to train a self-driving car, and we want to use the policy gradient algorithm. The agent here is the car, it's the vehicle itself, right? The environment is the world in which the vehicle drives. The states are all of the sensory informations that the vehicle sees, so it's coming from the cameras, the LiDARs, the radars, etc. The actions, right? These are the steering wheel angles. We'll think of it simply just in terms of steering wheel angle. Let's not think about speed for now. Let's just only think about steering wheel angle. And the reward, let's think of a very simple one, which is just drive as far as you can without crashing, right? So we're not optimizing for obvious things like comfort or safety. Let's just say let's drive as far as you can, not crashing. Implicitly, you will care about safety, right? Because you can't drive far without being safe to some degree. Okay, so let's start with this example. So how would we train a policy gradient model in this context of self-driving cars? Let's start with initializing the agent on the road. Okay, so we'll put it in the middle of the road and we'll start this system off. We'll now run a policy The policy here is a neural network, so we'll run forward the policy. This is called a rollout, so we'll execute a rollout of this agent through its environment, and we'll see kind of the trajectory of the vehicle over the course of training, right? So this policy has not been trained, right? So it didn't do very well. It kind of veered off and crashed on the side of the road. What we're going to do here is now take that policy, or take that rollout, I should say, and record all of the state action pairs. So at every state, we're going to record what that state was and what the action that our policy did at that time step. Now, something very simple. The optimization process in policy gradients is just going to assume the following, that I'm going to decrease the probability of everything that I did in the second half of my rollout because I came close to that crash, and I'm going to increase the probability of doing everything that I did in the first half. Okay, so is this really a good thing to do? It's probably not the optimal thing to do, right? Because there could definitely be some very bad actions that you took in the beginning of your rollout that caused you to get into a bad state, and that caused you to crash. So you shouldn't necessarily increase those beginning actions. But in reality, remember, you don't have any ground truth labels for any of this, right? So this is a reasonable heuristic that in expectation, it actually works out pretty well. And repeat this process again. So you decrease the probability of all of those things that came towards the crash, and you increase the probability of everything that came in the beginning. And now the policy or the agent is able to go a bit farther. And you do this again, and you keep repeating this process over and over again, and you'll eventually see that the agent performs better and better actions that allow it to accumulate more and more rewards over time until eventually it starts to follow the lanes without crashing, right? And that's exactly the policy gradient algorithm. I've left out kind of the exact loss function, but we'll talk about that in 1 second. And the remaining question here is, how can you actually update the policy based on those rollouts that you're observing? So based on those state action pairs that are being observed by the model as a course of the rollout, we're going to now increase the probability of everything that came in the beginning and decrease the probability of everything that came at the end. So this is really the last critical question of how do you do this in practice, right? So let's look at the loss function for doing that optimization, decreasing the probability of everything that came close to the crash, increasing the probability of everything that came in the beginning. So the loss consists here of two terms, right? So the first is this log likelihood term, right? This is going to be selecting an action that was chosen for this particular state. And then the second is going to be that we multiply it by the total discounted reward, R of t. Okay, now let's assume that we get a lot of reward for an action that had a very high log likelihood. So it had a very high probability, and we got a lot of return, a lot of reward. So that's great, because when you multiply those two numbers together, you're going to try and optimize that action even more to happen on the next time. But now let's assume you took an action that resulted in a very negative return. That would mean that you're now going to try, those will be multiplied against each other, and now you'll try to decrease the probability of those actions from happening again in the future. So when you plug that loss into the gradient descent algorithm, right, that we've been using as part of all of the trainings for all of the neural networks that we've seen in this course, we're going to see now the policy gradient algorithm, the policy gradient itself, right? So it's the gradient of that policy term highlighted in blue, and that's exactly how this algorithm got its name. So I want to talk a little bit now on how we can extend this approach to perform reinforcement learning in real life, right? And I want to think specifically in the context of this use case that we had gone through with self-driving cars for a second, right? So if we wanted to deploy this exact algorithm as we've described it in the real world, which of these steps, I guess on the left-hand side here, this training algorithm, which of these steps do you think are the ones that would kind of break down in real life? Yep, I heard. Yep, go ahead.
Recording all states.
Yeah, I think so. Recording the states is okay, right? So why do you think this?
Because I feel like when we're looking at the car example,
Yeah.
The path is continuous, and so like the path buffer we choose to look at, we can constantly decreasing it, right? So like the size of the magnitude of the states that can keep increasing.
Yes. Yeah. So as you basically the point is that if the car gets really good over time, then recording the states will be harder and harder because you have to store them all in memory. That's true, but it would also be a problem in simulation as well, right? You'd have that same problem. So there are tricks to get around that. Maybe you don't store all of the states. You only optimize a subset of them. Yes?
We run a simulation with the original states in separate contexts, like driving.
Yes. So reproducibility is a problem if you're in simulation. If you're in the real world, it's even harder, right, to reproduce the rollouts. That's true. Yes. Exactly. So yeah, number 2 is the real problem in the real world, right? So if you wanted to do number 2, it involves crashing the car, right, by definition. So, and that's only for one step of the algorithm, right? So it's a lot of bad things. You don't want to train your car to learn how to drive just by collecting a lot of data of crashes, right? So this, even though in theory all of this sounds really great, in practice, it doesn't work so well for real world, let's say, autonomy situations. One really cool result that we had created actually here at MIT was this simulator, which is hyper photorealistic, right? So it looks like this. These are simulated scenes of an autonomous vehicle driving through these environments, right? And these are basically environments that you can train in a way that is safe to crash, right? These are built from real data of the real world. So you'll see, you might even recognize Mass Ave in some of these, right? So it's right here at MIT. And the beautiful thing is that if you can have a simulation environment which is safe to do step number 2, right, to do this crashing behavior, essentially, then this type of problem is really well suited. The only problem then becomes the photorealism, right? You need your simulation to accurately be faithful to reality. But in these types of hyper photorealistic simulators, right, like this one that we had created here at MIT, the agent can indeed be placed inside the simulator, and it can be trained using the exact same model and the exact same loss function that we had just seen as part of this class. And then when you take those policies trained in simulation, you can put them on a full-size car in the real world. So now this is running in the real world, and they can drive through roads that they've never seen before, right? So very powerful idea, going straight from sim to real. And this was actually the first time that an end-to-end neural network was trained in simulation and could drive in the real world on a brand new road. And that came right here from MIT. Okay, so now we've covered the fundamentals behind value learning and policy gradient optimization for reinforcement learning approaches. What are some more exciting applications and advances? So for that, I want to turn very quickly to the game of Go, which has gotten a lot of interest over the past few years. So the game of Go is basically where RL agents want to learn how to execute actions on this board game, right? It's a strategic board game to test against human champions, their performance. And what was achieved several years ago was a really exciting result because, this game of Go is has a massive number of possible states. It's a 19 by 19 board game. The number of possible, or let me start with first the objective. The objective of the game is to basically collect more area on the board than your opponent, right? So you have 2-player game, white and black pieces, and the objective is to basically occupy more territory than your opponent. Even though the grid, right, so the environment looks a lot simpler than kind of our real-world environment. It's just a 2-dimensional grid and it has 19 by 19 squares. Go is extremely complex, even despite all of that. And that's because of the huge number of different possible board positions itself. So in fact, in a full-size board, there's a greater number of legal positions than there are atoms in the universe, right? So the objective here is to see if you can train an AI that can master this game of Go and put it up against human agents and see if you could beat even the gold standard of humans. So how can we do this? So a couple years ago, this was an approach that was presented. And the way it works is that you can develop a reinforcement learning policy that is actually, at its core, it's not at all that much different from exactly the techniques that you've learned about today. So first, you'll start by training a neural network that will watch games of humans playing the game of Go, right? So you'll train a network that is now supervised. This is not a reinforcement learning model. You'll just record a bunch of humans playing the game of Go. You'll record the states that they were in and the actions that they took, and you'll train a supervised model that will mimic those actions based on those states. So this is, so far, no reinforcement learning. You're just building an imitation system, essentially, right? So this will never surpass humans, but you can use it in the beginning just to learn some of the human strategies and techniques just at the beginning of training. The next step is to use those pre-trained models that were learned by watching humans and actually now play them in a reinforcement learning fashion against each other, right? So it's this idea of self-play that you can now take two models that have some very basic idea of how to play the game of Go, and you put them against each other, and they play the game of Go against each other, and the one that gets the reward is going to be the one that wins the game. And you're going to increase the probability of all of the actions that the agent that won, you will increase all of their actions, and you will decrease all of the actions of the agent that lost the game, right? Regardless of where, in the game they won or lost, all of the actions of the loser will be decreased, all of the actions of the winner will be increased. Very simple algorithm. And in practice, you run it for millions and billions of steps, and eventually you achieve superhuman performance, such that you can actually get some intuition about how to solve the game, such that you're not only looking at state in, action out, but also you want to achieve this state in, value out. Like, how good of a board state are you in based on the state that you currently see yourself? So a recent extension of this actually tried to explore what would happen if you abandoned kind of the imitation learning part in the very beginning, right? So the imitation part is where you watched a bunch of these human players of the game and see if you could bootstrap, essentially, the beginnings of the learning of this model from the human experts. So the question here is, can you start from a completely random network, still keep all of the self-play and the reinforcement learning, but you now start from a randomly initialized model? And what was shown is that these types of scenarios are also capable of achieving superhuman performance. They take a bit, obviously, longer to train, but it's possible to train them entirely from scratch with absolutely no knowledge of the games, such that they can overtake human performance. And in fact, they even overtake the original models that were bootstrapped by human performance. So the human kind of imitation in the beginning of learning helps in the beginning just to help accelerate learning, but it's actually quite limiting, right? Because oftentimes these models can figure out new strategies to these complex games that we as humans have not created yet, right? And you can see it now, that same idea is being deployed on a variety of different types of games, right? From Go to chess and many others as well. It's a very generalizable strategy. But the remarkable thing is that, the foundations, the way those models are trained is nothing more than policy gradient optimization, exactly in the way that we saw today. No labels, just increase the probability of everything that came with a win and decrease the probability of everything that comes with a loss. So with that, I'll just briefly summarize the learnings from today. So we started just by laying the foundations a little bit, defining all of these terminologies, and thinking about reinforcement learning as a completely new paradigm compared to supervised and unsupervised learning. And then we basically covered two different ways that we can learn these topics and learn these policies, right? We covered both Q-learning, which covers the model and how the model can output Q values for each of the possible actions. We talked about disadvantages and how policy learning could overtake some of those problems that comes with Q-learning, and how you can achieve continuous value reinforcement learning and also stochastic action spaces and so on. So a lot of exciting advances from policy gradients that can come in that field as well. And I'll pause there. The next lecture will be Ava, who's going to share new frontiers of deep learning and kind of all of the new advances. So it's the more recent, I guess, couple years of what has been going on in this field. And yeah, we'll just, as always, take a couple-minute break, switch speakers, and thank you.